In geometry, sometimes we face problems that I like to call shadow problems. In this example, Maya is 1.5 meters tall, and her shadow is 0.8 meters in length. The school Maya attends has a shadow that is 2.4 meters in length, but we don't know how tall it is. Although this doesn't look like a problem that involves two triangles, it really is. We could draw a line that would connect the top of Maya's head to the end of her shadow, and we could draw a line that would connect the top of the school to the end of the school's shadow. We would have two similar triangles. There are two ways this question could be asked. One way is to ask you for the height of the school as your final answer, but the question could also ask you to give the proportion that could be used to find the height of the school. In either case, I recommend solving it the same way, to carefully build a proportion. Knowing that this is a direct proportion, I use the methods that I always use to build my equation. I look at the numbers that I have, and I find the two numbers that I know must be similar. In this case, the length of the shadow and the length of the bigger shadow must be similar. So my habit is to put those two numbers together on the left, and I like to put the smaller number on the top. Now there is a third number that's given, and it is the height of Maya. That number has to be kept together with the length of Maya's shadow. The way I like to explain this to myself is, because these two numbers are both sides in the same triangle, they should be together. Since the length of Maya's shadow is on the top, the only way I can put the 1.5 into the proportion and have it be together with the 0.8 is to put the 1.5 on the top. This is the method that I always use to solve direct proportions. The x goes in the last remaining spot. Now we use cross multiplication to solve the proportion. The top times bottom gives me 0.8 times x. And bottom times top gives me 2.4 times 1.5. .4 times 1.5 is 3.6. And when I divide both sides by 0.8, x is isolated and is equal to 4.5. If the unit of measure given in the problem was meters, then x is equal to 4.5 meters. If we were asked to give the height of the school, we have our final answer and we are showing all of our calculations. And if we were asked to give the proportion that could be used to solve for the height of the school, that is this equation right here. This is how we do shadow problems. Here is another example of a shadow problem. In this case, Hunter has a shadow that is 2 meters in length. The basketball hoop has a shadow of 4.5 meters in length. The basketball hoop is 1.8 meters tall. But we're having trouble finding out how tall Hunter is because he won't stay still long enough for us to measure him. We did succeed in measuring his shadow, so we have enough information to build this direct proportion. The 2 meter shadow must be similar to the 4.5 meter shadow, so I'll put those two numbers together with the smaller one on top. The 1.8 meter height of the basketball hoop must be kept together with the 4.5 meter length of the shadow because they're part of the same triangle. To keep these two numbers together means I have to put my 1.8 on the bottom. My x goes in the last remaining spot. Cross multiplying, bottom times top gives me 4.5x. Top times bottom gives me 2 times 1.8. 2 times 1.8 is 3.6. And now I have to divide both sides by 4.5. These cancel. My x is now isolated and is equal to 3.6 divided by 4.5, which is 0.8. If I am asked for the height of Hunter as my final answer, all that's left is to put the unit of measure, which is meters. And if I was asked instead to give the proportion that could be used to find the height of Hunter, this equation is that proportion.